Can't say I'm a big fan of the textbook organization and how it talks about this material. So chapter 4 and 5 are very much related to each other. So we're going to end up bouncing back and forth between them, looking at the different levels of complexity. So these are just kind of suggested problems that I did one semester. You do not have to do these. Do not turn these in. I'm not grading them. I'm not looking at them. They're for you to do extra work on top of the online homework. The online homework should be available already. In theory, you guys have already started looking at that and started working on those problems. Right? So make sure that you're paying attention and keeping up with the online homework. So in general, it's the first half of chapter 4, followed by the first half of chapter 5, going back to chapter 4, and then going back to chapter 5, okay, to finish it all out. Okay? And that's because largely the first half of chapter 4 gives us some basics that we can kind of manipulate and deal with relatively okay. And then the second half of chapter 4 usually blows people's minds. And there's no real sense to destroying your mind before we move into chapter 5. Right? So we're going to talk about kind of those trends. We're going to go back and forth within these sections. Where it all starts is coming up with kind of our understanding of atoms and periodic law. Okay? So Dalton atomic theory. So Dalton went through, took a look at all these different combinations of things that they already found, and had been able to boil them down into what he presumed were indivisible structures, so the smallest atomic particles. And he came up with a periodic table and with some relative compounds. So his periodic table in the early 1800s was composed right there at the top. Okay. Looks kind of simpler and kind of more complicated all at the same time. You got a whole lot less elements to worry about, but the symbols used aren't the most appropriately nice as far as symbols go. So what he ended up having to do to build these structures would be take one of those symbols and match it with another symbol, or take two of those symbols and match it with another symbol. And in that way he could represent compounds. And so that's what's being shown underneath, is those individual compounds. He was able to do this because he came up with certain theories and rules behind how you go through and build things. So he had 5 main rules. An element is composed of tiny, indivisible, indestructible particles called atoms. So when we look at an individual element, we can then take a single atom of that, which is just the smallest piece of it, and combine that with other things. Right? So all atoms, once we have just a single element, of the same element are identical and have the same properties. Okay, so if I take hydrogen atom A and hydrogen atom B, they will have the exact same physical properties. At least that's what his theory was. Atoms of different elements can then combine to form compounds. So we can take, say, 2 atoms of hydrogen and an atom of oxygen to make water, okay, or H2O. We could also then go through and take 2 atoms of hydrogen and 2 atoms of oxygen, and we can make a new compound, H2O2, okay, also known as hydrogen peroxide, not a particularly nice compound. So using just the same elements but in slightly different ratios, we can get vastly different compounds. All compounds within an individual class will have the same properties as well. Okay, so they have the same number of atoms in whole number ratios, and they will then carry kind of a new system of properties out of it. Okay? So for instance, if we take a look at water, all molecules of water exhibit the same general features as any other molecule of water. Okay? We can then potentially combine those in different ratios, like I said, for H2O2, and that's what's happening in 5. So he kind of boiled this down and gave it a somewhat simpler system, because before this, we're just mashing stuff together and seeing what happens. So we kind of came up with some rules and understanding behind this. So one way to look at it would be kind of, again, using pictures. If we look at the picture to the far right with the sun, we can break that image of the sun down into the component pieces that made it. We've got all those triangles and that circle. And to make that sun, I need exactly 7, 8 triangles and 1 circle to go through and put that together. So we've got these exact ratios to build our larger structures. Are all of Dalton's rules actually true or valid still today? Some of them, but most of them actually have some kind of problems. Okay? An element is composed of tiny, indivisible, indestructible particles. Is that true? No, because we have... Yes, we have quarks. Way to jump right to the extreme, but yes. We've got protons, neutrons, and electrons, okay, which you haven't heard about officially yet in this class, but we can subcategorize our elements down into those pieces. Okay, so we can divide those up. Are all atoms of the same element? Do they have the same properties? For the most part, yes, but we do run into this issue of an isotope. Right? Again, you don't know that, but we've got isotopes that make different elements or different atoms of the same element have slightly different properties. Right? Atoms of different elements combine to form compounds. Yeah, that's true. That still holds true today. That's nice. You got something right. Okay, 4. Compounds contain atoms in whole number ratios. Absolutely. Still true today. Okay, and then that last one, we can form different compounds. So really where he ran into issues was the division process. How small can we possibly go? Okay? And that's that process that we're really talking about in chapter 4 and where those things came from. As we move towards the end of the 1800s, we run into Thomson. So Thomson was able to discover the existence of really an electron, and thereby the existence of a proton. Okay? And he was able to figure out a relative charge between these two. And what I think is more fascinating about this is what this discovery really hinged on. Because we think about science, we think about these big, great, grand, awesome ideas, okay, and how cool all the science and mathematics was behind it. But what allowed Thomson to discover an electron? Any ideas? It's not in the book. A vacuum. That's all he needed was a vacuum. Okay, why? Well, if we look at these subatomic particles, the pieces that make up atoms, how stable might we predict them to be? Should they be really stable, really unstable? Really unstable. Right? And there's a couple reasons that we can use behind this. One reason is, do we see protons or electrons on our periodic table? No. Okay? So they don't exist on their own. They have to be combined in the proper ratios to make our atoms or our elements. Okay? Then the question becomes, well, why? Well, one reason can come from their charge. They are all charged. We tend to think, oh, charge isn't that big of a deal. Well, anybody that says charge isn't that big of a deal, stick your finger in an electrical outlet. What does the electrical outlet have coming out of it? Electricity, which is made up of electrons, which have charge. Okay? It's ultimately that charge that is exceptionally high. Don't stick your finger in an electrical outlet. I did not tell you to do that, by the way. Don't. Okay? That charge is really, really bad, very, very high energy. So if we're going to try to find these things of very high energy states, we have to get them by themselves. Because what happens if something's in a high energy and it hits something else? It's no longer in existence. It's now reacted with whatever that was, and it's become a new, larger piece. So to discover our electrons or our protons, these very high energy reactive particles, we have to isolate them. Okay, well, how can you isolate them? There needs to be nothing around them. If I just take a box, what's in that box now? Air. Is air a particle that could potentially interact with my electrons or protons? Yeah. So if I want to be able to find an electron or learn anything about it, I have to remove all of the air. But how do you remove air if you don't have a vacuum? Sucking on it doesn't work quite well enough. Okay? You need a much stronger vacuum than that. So that was one of the biggest holdups on the discovery of our electron, is because we have to have a vacuum. Without that vacuum, as soon as I try and do anything that might generate these high energy species, it's now going to react and I can't evaluate it anymore. Okay? So kind of a neat process. So what happens? Well, they generate with this vacuum. They take a glass tube and they pull all the air out of it. And this becomes interesting. They then pump electricity through it. Okay, so at one end of this, we've got a big source of electrons, or a big source of negative species, electricity. And at one end, we have a positive source. And at this point, we don't know what electricity is. It's the flow of these electrons. We just know that it allows things to happen. Okay, and if we had a wire there, we wouldn't see anything exciting. Electrons jump through, well, whatever. But when they put it into a vacuum, that's when things became a bit bizarre. Because when it's now in a vacuum, can the electrons move? Well, if there's nothing there, it can't jump. It's not like it's the wire causing the electricity. Okay, so theoretically, if we plug this up, we would expect to see nothing. And what ended up happening instead was they saw this beam of light. Seemed to be skipping through, moving from that negative part of our cathode to the positive end. Okay. That beam of light had to come from somewhere, but if we've pulled everything out of it, the only place it could have come from was our electric current. So we now have a theory that we've got particles that are giving us electric current that are now negatively charged. And these negatively charged things are ridiculously tiny. Okay, so we now have this idea of a negative charged species. Well, it can't be any of our elements, because our elements have all been removed from our tube. So now we have a smaller particle, okay, and that's our electron. Okay, well, what was this tube that they were playing around with? Kaleidoscope, interesting idea. Cathode ray tube. It's the beginnings of television. Okay, your old school televisions are CRTs, okay, cathode ray tubes. You have a very crude cathode ray tube. So we now have the discovery of electrons through discovery of TV. How cool is that?
In the 1800s, too.
In the 1800s, yeah. And they came up with all sorts of fancy names for this, but this is ultimately how we pick up an electron, okay, the existence of an electron, okay, all through Thomson. So Thomson goes through and says, okay, I'm going to come up with a theory to explain what's going on here. If we got these negatively charged species, but I look at an atom or an element that isn't charged, then the atoms or elements must be made up of something more than just electrons. They have to have something balance out that negative charge. All right, well, there's the existence now of a positively charged species, or a proton. All right? And in his theory, he just said, well, I'm just going to say they're free-flowing. We take a look at a giant atom, and we got a bunch of electrons and a bunch of protons just kind of floating around near each other, okay, canceling out that charge. So we get this kind of big sphere. He went through and discussed this as the plum pudding model of the atom, which I'm sure there's a reading question on in your homework, but I never seem to remember it right. You've got the pudding that is your sea of protons, or your positive charge, and then you have the raisins that are your electrons, that are little chunks floating in it. Okay, that's your plum pudding theory of the atom. Okay? And really all he could pick up out of this was something about the mass of your particles and the charge.
So the pudding is the same protons and the raisins are electrons?
I believe that is true, yeah. You may have to check that on me.
All right, now
Okay.
That sounds right.
You could just as easily swap it the other way around, though. Okay?
I mean, what's one plus?
What makes this even more interesting is that we could then jump to Milliken. Okay, Milliken, Fletcher, and then eyesight in practice, which is another kind of fascinating experiment. This experiment isn't discussed in your textbook for some reason. I don't know why, because it's kind of neat. What they were able to do is to determine the charge on an electron, okay, the actual charge on the electron, not its relative charge. So in our previous circumstance, we really only had a relative charge. We had something that's negatively charged, which means we have something that's positively charged to counteract it. Okay? So Milliken was able to set up this fancy experiment. Okay? What he did was took oil, okay, and he just sprayed a fine mist of oil. Well, oil has friction associated with it, and it generates a charge. Okay? And they were able to see that it has a charge associated with it. He then took that spray and set up a tiny, tiny little slit in the bottom of his container so that when he sprayed in, 1 or 2 droplets maybe would fall through that little hole. Well, due to the static charge, they are now charged species. So what he did just underneath that was put in an electrical plate. Okay, why would he put in that electrical plate? Well, if your electrons are negative and they start to fall, what could you put at the bottom of that plate? Put in a positive. What's going to happen to the electrons fall now? It should go faster. It's going to slam against the plate. Okay? What could we do to adjust that? Put a negative at the bottom. So as soon as the droplet falls through, you can now start to up the voltage on your plate. And now the bottom of the plate starts to become negative. What happens when the electrons get near more electrons? They repel. And you dial that little dial till eventually your particle stops moving. Okay? At this point, you've now counteracted gravity. We know what the force is that gravity exerts. We've got mass and gravitation fields. And we know some understanding of electrical currents. We can then calculate what the exact charge is on that drop by then also guessing, or not guessing, but looking at the size of the drop through your stupid little eyepiece and approximating the size of the drop to then determine the charge on the drop. Okay? So just by looking at oil fall and then catching the oil droplets in air and then studying those oil droplets ridiculously close, they could pick up the exact charge on an electron by doing this probably hundreds of thousands of times.
So does this kind of almost relate to magnets in a sense?
It's the same idea as magnets.
So like if you like have the 2 negative ends, they'll never touch, but if you put the negatives with the positives,
They will attract. Yep. It's the exact same process. And you're doing the same kind, you're taking advantage of that process here. So it's kind of a neat idea. So Milliken gets us that we have a charge on our electron. We'll notice that is a very small charge, and we've got coulombs. You don't really need to know that other than we now know its charge. The next big scientist to come along was Rutherford. I usually like to describe the context of this experiment in being that Rutherford and Thomson didn't like each other. Okay? And you might come up with reasons or see why I would think this. Okay, so Rutherford looked at Thomson's model, the plum pudding. We see that up at the top. Okay, so if we take just a thin sheet of any element we want, okay, most of it is going to be filled with things that have no mass. Because protons don't have a large mass, electrons don't have a mass. And if I now fire a particle at this sheet, what should happen? Right, we look at the drawing, what's happening with the particle? Okay, those particles pass directly through. So if Thomson's model is correct, what happens when Rutherford does this? Well, he just sees the particles pass straight through. The end of the experiment. Thomson's model is now valid, and we now have the plum pudding model of the atom existing for here to eternity. Okay. So what Rutherford and his group did was put a thin piece of gold foil, okay, and they set up their experiment where they then took their source of these alpha particles, which is just a high energy radioactive particle, and then fired it at that gold beam. What they then did was set up a detector. And on the outside of this, we have a detector that's going to then look for those particles. So if it hits, it glows. Oh, there it goes, it glows. Right? Why do you think Rutherford might not have liked Thomson's model? If he liked Thomson's model, where should the detector be located? Immediately behind it, and nowhere else. Because if he liked it, where are those particles going to show?
That's just not good science.
Immediately behind it. And it doesn't have anything to do with good science, unfortunately. We would expect it to go straight on through. And he could verify that. Because you put the detector up, you notice that most particles hit directly behind it. Rutherford questioned the validity of that model. And so instead of having the detector only be immediately behind the foil, he wrapped it all the way around. Okay? So now what happens? Well, if Thomson's model is correct, what happens? Our particles pass straight through and we hit our detector, right at the very back end with no change. What was the actual result? Didn't see that. They saw a bunch of deflections. Right? They saw a bunch of targets being hit in places that make no sense if our atoms don't have any real condensed center of mass. So what does that then mean?
Particles like electrons and protons are condensed, so it just kind of
We have to have something condensed into the middle. So instead of having this plum pudding model, we've got something where everything is mashed really tightly into one space. The question then becomes, well, what would that thing be? Okay, well, it turns out that alpha particles have a charge associated with them. They are positively charged. What would happen if our nucleus was all electrons? They would just stay there at best. Okay? Since we're firing positive charge, though, okay, we would expect that they would stay. And since we're now seeing reflection, what does that mean our nucleus needs to be made of? Positive. It has to be the opposite. Okay? If it's negative, it stucks, or it sticks. If it's positive, we can get that like charge repulsion. So if our alpha particle happens to come in at the perfect alignment to see that nucleus, it can then repel off of it. And if it repels, we see a detection happen on the other side of our foil than we would have predicted. That tells us that whatever's in the middle is positively charged and has to be of a significant mass. Because if it wasn't significant, it would just push our foil all the way through as well. Okay? This is the existence of our nucleus. And that nucleus is then positive. Another little side rant. What are alpha particles? Anybody know that one, actually? Alpha particles are actually helium nuclei. Okay? They are a byproduct of nuclear radiation. So some elements will decompose, and in that decomposition process, they can emit radiation. One of those radiative forms is an alpha particle. Okay? Helium nucleus. So we're looking at just the center of a helium atom, which means it's just positive. Well, where do we get this? Where do we get radioactive stuff from? It's going to come back to making it. Some of our elements are radioactive. If we get far enough down on our periodic table, they are radioactive on their own. The issue with that radioactivity, though, is that as they decay, they change their state to a new molecule. So if we just go into nature and grab a random radioactive sample, it's going to be giving off a lot of different types of radiation. Well, if we have different types of radiation, do we know exactly what we're hitting at the gold foil? No. Which means, can we draw any conclusions about what's happening out there? Because maybe the particle I'm firing is actually negative and not positive. Well, that's a significant change in my understanding. So to be able to do this experiment, we have to have a pure radioactive source. All right, that's a bit tricky.
radioactive. What is the true actual meaning of it?
It's a nucleus decomposing. Yeah, it is literally, the nucleus is so large that it falls apart. And as it falls apart, it spits out those pieces.
That's like radiation.
Mm-hmm. All that radiation stuff is, yeah, all back to radioactivity. Nucleus falling apart.
Like a name for like weak something?
What's that?
Like an official name for like weak something and strong something?
You can look at the strength of radiation that you can find. It's usually measured in a term known as Curies. Does that name ring any bells?
Is that because Marie Curie died discovering?
From Madame Curie. Okay. This is sort of a soapbox moment. The only reason Rutherford can do this experiment is because he has a radioactive source. That radioactive source down here was radium, okay, which was purified by Madame Curie. Why is that of particular interest? Okay. Number one, the only way that he would get that source or that information on how to purify it is if she released that information. If some scientist discovered something these days, big phenomenal idea, what are they going to do to it first? Patent the process. And what does that do to the scientific discovery from the future? Kills it. What did Curie do when she figured out this purification scheme? She released it to the public and gave everybody free access to it. That then gives Rutherford the ability to generate his pure radium sample so that he can then run his experiment and actually get this tested. Very anti-patent, this woman. Very cool woman in that respect. Take this a step further. When did she do this? Early 1900s. Why might that be relevant?
She was a woman.
Why is that important?
They weren't allowed that.
You couldn't even vote as a woman. And yet she was able to discover radium, which allowed all these other male scientists to come up with these cool discoveries. Okay? Not only could she not vote, but she actually released this information freely to everybody else so they could have access to it and be able to process this. Okay? Couldn't even vote, but she makes a massive discovery. Such a massive discovery that what do? Or what did the Swedes or the Swiss do? They give her a Nobel Prize. Okay, a Nobel Prize in physics. A little while later, what happens? She makes some more discoveries about radiation. And what do? We give it another Nobel Prize in chemistry. She is the only person to have 2 Nobel Prizes in science-related fields. Okay? All before women could vote. Okay? Given absolutely zero respect in her field, and yet she's making these massive contributions just by forcing herself into the field and doing that research that she wanted to do. Okay? Absolutely amazingly impressive. Okay? And as far as that whole kind of, well, we gave her a Nobel Prize, she can't have been that looked down upon. She was a French scientist. There's the French Consortium of Science people, whatever you want to call it. I'm sure they have a fancier name. She was not granted access. She was not allowed to be a member of the French Science Society because she was a woman, okay? Which is ludicrously stupid. Okay? But that's kind of how science is built. So that's why we need new minds getting into science and pushing those boundaries and showing that everybody can contribute, okay? Even through our failures. Because what was her ultimate failure when it came to this? She didn't realize that radiation was ridiculously dangerous, and she ended up dying due to radiation exposure. Okay? Yeah. Yeah. So, fascinating woman, very important to our overall understanding of arguably not just chemistry, but the existence of a nucleus. Okay? Our understanding of atomic structure can really come back to her discoveries and her work in radiation. Yeah.
Why is radiation just so terrible for you?
Extremely high energy particles is what it comes down to. So if you think about ultraviolet light, so ultraviolet light, relatively dangerous, right? We put on sunscreen, we wear clothes, kind of protect ourselves from the light from the sun. If you look at radiation, nuclear radiation, the energy is like billions-fold higher in energy than UV radiation. So it's a lot higher in energy, which means it can do a lot more damage.
So like what kind of radiation would that be?
X-ray, and yes, they are dangerous, which is why you'll notice that almost all techs wear lead vests or hide behind walls. They tell you it's perfectly safe in limited exposures, because in limited exposures, you may mess up one cell through a mutation, but then that cell dies. Oh well. If you're constantly exposed, the odds that one cell actually survives and becomes cancerous becomes astronomically higher because of that continued exposure.
It also makes you sterile.
It can do a lot of things.
That's why they give you that little pad to wear.
A lead vest? Yes. So if we take a look at some kind of scale ideas with about our nucleus, an atom has a diameter of about 10 to the minus 8. The nucleus is a diameter of 10 to the minus 13. Minus 8, minus 13, oh, that's 8 and 13. It's only, what, 5 units difference? That's not a big deal. If we scale this up, if the atom is the size of the superdome, the nucleus is the size of a marble sitting inside the superdome. Okay? So this is a pretty significant difference in size. Okay? That's why powers of 10 we tend to kind of lose sight of. Go back to our national debt again if you wanted. Okay? That whole factor of 10 just disappears. Okay? So Rutherford went through, said we had to have neutral particles as well as these positive and negative particles. That's interesting. Why would he bring in the neutral particles? Like charges repel. We did the same thing with Milliken's experiment, chase the electrons away from each other. So what happens when we move into Rutherford's model? Well, he said we take all the positive charge in our atom and we smash it into one tiny little place. Okay? Well, one tiny little place with a lot of positive charge, what's it going to do? Explode away from each other. So we need something in there to neutralize that charge. Okay? Since we know the electrons are on the outside, it can't be electrons, we need to have some kind of glue to go through and hold it in. What is that glue? That's the existence of your neutron. Yes?
Doesn't the neutron also keep it from like falling in on itself, like the electrons from coming into the nucleus?
I've not heard that, so I can't say yes or no either way. But I would lean towards no. Do I actually have? Yeah, I didn't think I did that. So we're really looking at that nuclear repulsive force. We're trying to hold those together. They were experimentally discovered by James Chadwick. Not that big of a deal, but I mean, it's a neat fact. Now we've got a list of all of our subatomic particles. So we've got electrons, protons, and neutrons. And we're going to have a bunch of information that we need to know about where these things are and what stuff do we know about them. So our electrons are found outside our nucleus. Our protons and our neutrons are found on the inside. Okay, this becomes relevant when we think about bonding as well. Relative charge. Our neutron will have no charge. Okay, absolutely nothing. It's only there to act as a glue to prevent the positive charges from exploding away from each other. Our protons will have a positive charge, and our electrons have a negative charge. Okay? These positives and negatives are not absolutes. They're relative to each other. Okay? So the actual charge was what Milliken discovered. That was that crazy weird 9 times 10 to the whatever, negative 17 stuff. Okay? What we're looking at is the relative charge. So our electrons are negative, our protons are positive. If we now shift to the mass, protons carry a mass, electrons relatively not. And we've also found that our neutrons are roughly the same mass as our protons. So again, we're using a relative mass term here, using 1 as our normalized value for our protons and neutrons. What value should you memorize for your electrons? For the mass. Okay, there is a number associated there. The relative mass of an electron is 1 over 1,836. Okay. You're looking at adding a significant number of zeros there. Okay. For instance, we could say, I'll give you $1 plus an electron. How much money are you getting? $1 plus 0.0001. Okay. That carrying over doesn't really matter. Okay, so the mass of our electron, for all intents and purposes, is 0. Next part of this that might be helpful would be to recognize symbols. Okay, when we look at the symbol for hydrogen, what is it? H. Why do we pick H? Hydrogen is spelled with an H. What symbol do we use for electron? E, because electron is spelled with E. Right? So we've got our electrons, our protons, and our neutrons with those respective symbols. You'll notice that we'll show the charge for each of those elements, or each of those particles. The neutron, it's not necessary to show the charge on because it's 0 charge. It's neutral. There's no point in showing it We don't have to. Okay? You will also notice that our charge is located in all three cases where? Superscript on the right-hand side of our symbol. Charge throughout the rest of your chemistry career will always show up in the upper right-hand corner. Always. Okay? So we now have these basic pieces that we can then put together into making larger elements. Okay? Which now brings us to atomic notation. If we're now going to represent our elements, we want to come up with some way to look at the combination of all of these pieces and summarize that neatly and succinctly. Okay? So we've got some new terms coming out of this. We've got the atomic number, which is given the symbol Z for God knows what reason. And we've got the mass number, likewise given the symbol A. Okay? What those numbers represent are our protons and our neutrons. Okay? Remember, when we looked at mass, a proton and a neutron had the same mass. So when I'm looking at the mass number, that's going to necessarily imply the sum of the protons and the neutrons. Okay? I need to have both of those terms. You'll notice that we don't mention anything about the electrons. Why not? The electrons, with respect to mass, are useless. So we don't use the mass of our electrons when we're looking at our mass number. Is that a question?
The atomic number is the number of protons, right?
The atomic number is the number of protons, yes. It's one of those stupid memorization things that's just forgotten quickly. The next part is your atomic number, which is just the number of protons. That information is specified in the lower left-hand corner. Okay. Kind of a bit redundant. Why might it be redundant? If I give you the atomic mass, let's say 1 and H, what's the atomic number? 1. How do you know that? How do you know it only has one proton? Our periodic table is organized based on the atomic numbers.
So do we have them separated for when we get into isotopes? Is it?
The atomic number will not change for an isotope.
I mean the mass number.
We have the mass number separated because we can change the number of neutrons. Yes. What happens if I switch to now helium? The atomic number becomes 2. What happens to the atomic mass? Most commonly, it jumps up to 4. How did you know the 4? What do you mean right there? I can kind of accept that.
It's double, maybe?
It's on the periodic table. If we take a look at our periodic table, we've got the atomic number in the upper right-hand corner on our periodic table, and we have the atomic mass in the lower left-hand corner. We now have a way to look at our protons and our neutrons by looking at our periodic table. Okay, pretty helpful. The atomic or the mass number may change, so be aware of that. That value can change all over the place. Okay, if we go back to hydrogen, which I know a little bit more about, I can have the element of hydrogen. With one proton, it has to be hydrogen. Because as soon as I add another proton, it becomes helium. Okay. But does the mass have to be 1? No, the mass could be 2. In which case I have deuterium. Which I don't know how to spell, but I'm going to guess. What if it's 3? We now have tritium. Right? You notice we came up with these new names for it. Do we have to come up with new names? They're still referring to the element of hydrogen, just with a different mass. Why did we come up with new names? Because it's fun to make you think that we're always going to have new names for them. Those just happen to be super common ones because hydrogen we use in different isotopic forms fairly frequently. Okay, so that's the only reason they pick up new names. Most typically we'll refer to our isotopes based off of the atomic notation. Right? So tritium would most commonly be referred to as hydrogen 3. Really exciting. Okay? Being because it has the weight of 3. Okay? Its mass is 3. So what is our atomic mass? The number of protons and neutrons. So if we have 3, if I say hydrogen 3, what information does that tell me? Can I have 3 protons? 3 is the mass number. How do we determine the mass number? It's the sum of our protons and neutrons. If I have hydrogen, how many protons do I have? 1. If I have hydrogen 3, how many neutrons do I have? 2 neutrons plus 1 hydrogen gets me the 3. So the mass number is just the sum of the protons and neutrons. That information can be given in that upper left-hand corner or written out in kind of long form by writing out the element name. There is no unit associated with it. Okay, so let's take a look at, well, that's a bit silly. I guess we can do that. An example. What is the element represented here? How do you know it's silicon? So it's Si. How else can you know it's silicon? You look at the atomic number. What atomic number do we have? 14. So we go to 14 in the upper right-hand corner on our periodic table, and we are at symbol Si. There's our silicon again. Okay, what other information can we come out of here? What's our atomic number? 14. Okay, which means we have 14 protons. Okay, so our atomic number gives us the element, okay, our proton count. What's our mass number? 29. Is that the mass number on our periodic table?
No.
Huh. That's odd. I wonder why that doesn't add up. Nope. Nope.
Why is it flipped anyway?
Why is what flipped?
Because on the periodic table,
Never mind. I know what you're talking about now. Why is our atomic number and our mass number flipped when we look at our atomic notation versus our periodic table organization?
it's easier that way.
No freaking clue on that. But someone went through and decided to swap them. And
They just said screw science and do it anyway.
screw organization, maybe. I wouldn't go as far as screwing science. So our mass number, 29, is the number of our protons and our neutrons, which means our number of neutrons is we know 29 equals our protons, which we know in this case is 14, plus our neutrons, which means neutrons has to equal 15. Kind of the simple calculations that come out of this, allowing you to go through and figure these things out. Okay? Oh, shoot. I just deleted a quiz from it because I don't have enough little sheets of paper. Okay, so this may show up again at some time in the near future. Jumping to chapter 5. Well, you got the slides, they're posted online, you can read it there. We're going to jump to chapter 5 to look at some organization on the periodic table, which we've already started to allude to. Okay, we've got the atomic number, we've got the atomic mass. Okay, all of that is given to us off of our table. You'll notice that they list here on the periodic table atomic mass, whereas on those previous slides, did we refer to it as the atomic mass? It was the mass number, not the atomic mass. That seems a bit odd. Do you think there's a difference? Fortunately, there is. Okay, we'll address that difference in a little bit. They are related to each other, but they are not the same. The mass given off of your periodic table is the average mass for all isotopes of that element. Okay? So when we look at hydrogen, I just listed off 2 other types of hydrogen. We had hydrogen, deuterium, and tritium. All of them had different atomic masses. But what is the mass written, or sorry, mass numbers? What is the atomic mass written for hydrogen? 1.1 or 1.01. Yeah, it's just a 0. Okay. Why is it not exactly 1.00? We said we had deuterium and tritium in there, right? And deuterium has a mass of 2, and tritium has a mass of 3. So what's the average of 1, 2, and 3? 2. Still not equal to 1. Okay, what we have to realize is that you're looking at a weighted average. There is a lot more of hydrogen with mass 1 than there is of hydrogen with mass 3. That weighted average is a calculation that you will have to go through and deal with. Okay? We're not going to deal with it right now. I just want to make sure you're aware of that difference. So our periodic table is now organized according to our atomic numbers, okay, which allows us to go through and very quickly identify the amount of protons in an individual element. Okay, if we look at the atomic mass, we now have the average mass for that element. And so if I don't care about isotopic effects, that's what I'm going to end up looking at. Right? When do you care about isotopic effects? When you're dealing with radioactive species. What are the odds we're going to give you anything radioactive? Not very likely, which means very often all you're going to be dealing with is that number at the bottom as the average. Okay? Because it is officially a class where we're going to talk about it, you will have to run into it occasionally in lecture, but for the most part, you can just use the atomic mass off of our periodic table. So, what's our atomic structure for carbon? How many electrons, how many protons, how many neutrons? What's the easiest thing for you to pick out?
6 protons.
6 protons. Why'd you pick that out? Atomic number 6. Good jump. What else can you give me? How do you know the electrons? You can't tell me the electrons from the atomic mass. Tell me the neutrons from the atomic mass. You can't tell me the electrons. We've got 6 neutrons. We do have that issue with the 0.01. Okay, we'll just call it 6 neutrons. And we're really just saying 6 because that's as close as we can get. Okay, we'll ignore the kind of rounding effects that we'll pull off of that. How many electrons in this?
4.
Why 6?
You have to balance, otherwise you have an ion.
Remember, we said electrons and protons were highly unstable. We want to strive for neutrality. So if we're looking at just carbon on its own, how many electrons need to be present? 6 to balance out the protons. Okay? So we can pull that information relatively quickly off our periodic table. So our atomic number can give us both the electrons and the protons by kind of inference. Where we've got to be careful. What happens if this carbon is now charged? What charge? Good call. Let's say it's carbon minus 2. What's that? It needs to have more electrons than protons. So how can I go through and change this? Do I change the neutrons? No, because the only thing that's changing is the charge. Should I change the protons? Why not? If I get rid of 2 protons, don't I become negative 2? What's that?
It has to be carbon.
The protons define the element. If you change the number of protons, you no longer have that element. Okay? So what do we have to do to get to a negative 2?
Add 2 more electrons.
We need to add 2 electrons. But isn't adding the opposite of negative? Why are we adding? Yes. The electrons are negatively charged. which means when we look at the net balance, we've got 8 negatively charged species, 6 positively charged species. When we add that up, what do we get? -2. Let's run the math out. How many electrons do we have? 8. What's the charge on an electron? How many? What's the next one? Protons. How many protons do we have? What's the charge on a proton? +1 gets us our -2. Okay? Some people are able to see and deal with that math relatively quickly in their head. All we're doing is taking the charge balance of both our protons and our electrons. Be aware, you cannot change protons. The only thing you can change are your electrons. Otherwise, you're no longer looking at the same element.
So no matter what, if it's not charged to anything, the protons are going to equal the electrons?
If I write carbon with no charge in that upper right-hand corner, by definition, it has 0 charge. For it to have a 0 charge, how many electrons do I need?
Oh, that.
X times -1 plus 6 times +1 equals 0. What does X have to be? 6.
And you give it a positive charge, you just subtract electrons.
To get a positive charge, you now have to remove electrons. Exactly right. We said what happens if you have a negatively charged atom. So it was a new question, which is why I wrote the new question. C -2. Right. And actually, I want to add a little bit more information on this. What if there's no electrons? What do you mean, what if there's no electrons?
You have a positive charge of +6. That would mean you'd have to
There'd be,
remove
you'd have to remove all electrons.
all. So what happens?
What do you think would happen if we have a species that is +6? How stable would it be? Not very unstable. What's the first thing it's going to do when it encounters another molecule? Steals electrons. So even if we could get it up to that high of a charged state, as soon as it touches anything, it's going to start pulling electrons off.
Is that why a lot of the synthetically prepared elements on the periodic table have a lot more electrons than protons?
Nope. As we move further up in the periodic table, let's look at, anybody know the name for Lu?
Lithuania?
Since nobody knows, I think I've got it. Luteum. If we're taking it luteum, how many protons does luteum have? How many electrons? 71. What's the 174 mean? That's the sum of the protons and neutrons, not our electrons. You'll notice that as we go up in the periodic table, what happens to the number of neutrons in our elements relative to the number of protons? That gets higher. As we move to bigger elements, we have to add in a lot more neutrons than we started with. Why? We now have more positive charges getting close to each other. So we have to add in more neutrons, I see, to separate and get those positive charges away from each other. Okay? Which then puts us to the next issue. You'll notice that a lot of our elements down here are radioactive. Why are they radioactive? Because the nuclei is so big that those positive charges, okay, are starting to get too close to each other, they start shooting out. Okay? The way you can envision it is if we take two marbles, we can potentially glue those 2 marbles to each other. You can probably glue another one in, and another one, and another one. But if you get up to, say, 103 marbles, what starts to happen? Structural integrity falls apart. That's what's happening with our radioactive elements. That's what's happening with our synthetically made elements, is that they are so large that the glue no longer holds.
Why is that one not even happening, Tom?
It's so unstable they couldn't actually measure it.
Do you think there's, it's like really off topic, but do you think there's more elements that have been made, but we just can't afford to put a new periodic table in everything?
I'd say no. We're definitely running at the limit of our abilities. We'd have to find some other type of particle to act as a glue to hold it to get it bigger. Our neutrons are not going to be possible.
Are there like any like elements from like outer space that would be like on that table? Or like you need to start holding the table?
Meteors are largely composed of iron and nickel. straight off our periodic table. Stuff from outer space is the same composition. Different amounts for each, but pretty much the same compositions. And we can arrange them in different fashions, but that's about it.
How come the synthetic ones have their mass in parentheses?
Radioactive.
Didn't we just recently discover a new way of bonding by like vibrating?
Yes, there's a new type of bond that's going to be between atoms that's not within nuclei, though. I believe. I have to look at that closer, but I don't think it's nuclei interactions. Other fun questions on that?
How does your phone vibrate?
How does my phone vibrate? There's a motor inside that just moves. That's it. Yeah. Protons. So protons define what? If you change the number of protons, what have you done? You change the element. So our protons define the element. What do our electrons do? Change the number of electrons, what have we done? Change the charge. So our electrons ultimately define the charge. It's a little bit of a weird statement to make because to define our charge, we need both negatives and positives. Okay? But our negative or our electron contribution is really what's defining our charge. And our neutrons, we change the number of neutrons, what do?
Changing the mass.
We change the mass. So our neutrons really define our mass. Yes, again, protons contribute to mass, but our protons are primarily concerned about defining our element. Once we're in an individual element, we can't change the protons. We can change the neutrons, and we can change our electrons. Okay? So, we've got the neutrons within each of our elements. We run into this concept of isotopes. So all an isotope is we've changed the number of neutrons for an individual element. So in the case of hydrogen, we really have protium. Right? What we would typically refer to as hydrogen is commonly referred to as protium. And is very specifically referring to a hydrogen of an atomic mass of 1. Okay, or a mass number of 1. Which means how many neutrons does protium have? 0. Okay. Remember, your mass number is written in the which corner? Top left corner is your mass number. Your atomic number is the lower left. The mass number is composed of what? The number of protons plus the number of neutrons. If it's hydrogen, how many protons are there? If it's hydrogen, how many protons are there? 1. How many neutrons do we need to get 1 equal to 1? 0. How many neutrons are present in protium? 0. Okay. What happens when we move to deuterium? We have our mass of 2, which needs to equal our number of protons plus our neutrons. How many protons do we have? How many neutrons then? We necessarily need 1 neutron to make up that mass difference. Okay? Those two are called isotopes, okay, or referenced as isotopes, because we have a different number of neutrons associated with them. That's all the term isotope has to do with. Yes?
Why do we assume they're spherical?
You assume they're spherical. We don't assume they're spherical, actually, unfortunately. Okay? How many protons and neutrons does an atom of lead-206 have? What did we say we could translate this into? Lead is Pb. Where's the 206? Need to get written in. The 206 is the mass or the atomic number? Mass. Because if it was the atomic number, we'd have a hard time finding it, right? So our atomic number, were you actually right?
I think it's 124.
No, it can't be 124.
For the neutrons.
Oh, you did the, I just want the atomic number.
Oh.
Our atomic number is 82. Whoops. So how many protons do we have? 82. Straight off of our periodic table. How many neutrons?
124.
Did you really just do that math right? 82 plus our number of neutrons. Sure. What'd you say? I already forgot. 124. You have 124 neutrons. Really simple, straightforward question. What would your multiple choice answers be on the exam?
124, 82, 0, 2, 11.
I like the 207. Which then also means 125. Okay? All of those numbers would be floating in there. You have to make sure that you understand how to calculate it. Okay? That's why we stepwise dropped into our atomic notation and then moved through to our protons and neutrons to total it up. Okay? Questions? Oh, this will be ugly, but we'll go with it today for the moment and we'll come back to it. So, simple versus weighted average. A simple average assumes that everything is worth the same value. We have the same number of them. A weighted average takes into account the fact that we do not have equal numbers of each of the objects. Okay? The weighted average is calculated by multiplying the percent of that object as a decimal value by its value. And then we add all of those up, and we would get our weighted average. Okay, so for instance, if I take the average of 1 and 2, actually let's do this, 1, 2, and 3. What's my simple average? Okay, our simple average, we add everything up. 1 and 2 is 3, plus 3 is 6. 6 divided by 3 gets us 2. What happens if we now go through, that's not 1,000, if we have all of those values?
1.01.
If we go through and do our average now, we can just add all of these values up and divide by our total to get our value. So 4, 6, 7. Did I actually do that right? You're right. Thank you for the 9. 9 divided by how many values? 2, 3, 4, 6. And we get, assuming the 1.5 was right. Okay? So in that case, we again just went through and took all of our values and we calculated this as a simple average. Okay, this was our calculated value. The other way we could have done it was taking a look at what was the percentage of each of those in each of our calculations. How many times did 1 show up? 4 times out of how many options? 6. So we could do 4 divided by 6. There's our percent times the value, which is 1. Plus, how many times did 2 show up? 1 out of how many times? 6 times, times the value, 2. Plus, how many times did 3 show up? 1 out of 6 times, times our 3. And if we go through and do this, give me a second, you will get the exact same answer. So why do we choose to go through and do it this a seemingly long way to do it? Well, if I go through, let's see, do I have numbers here? Here are the numbers that I'm giving you. You have gallium-69 with a mass of 68.926 mass units and a 60% abundance. Gallium-71 with a mass of 70.925 and a 39.89% abundance. What is the average mass of gallium? We can't just take a simple average here. Because to do that simple average, I'd have to count every gallium-79 atom and every gallium-71 atom and get totals for each of those. How tiny is an atom? Really, really small. We can't actually count it. Okay? To actually get to a scale where we could actually even hold those amounts, we're looking at billions of trillions of atoms. So to be able to run an average with just counting those simple numbers doesn't work. We need to go through and use the weighted averages. So to go through and run this calculation, what do I then do? Same thing as we did before. How many times does gallium-69 show up? And say 60.11, what's that percent doing?
Over 100.
In a sample size of 100, it shows up 60.11 times. What was the mass of gallium-69? 68.926 AMUs. Plus, what was the percent or the amount of times that gallium-71 showed up? 39.89 times in 100 sample times its mass, 70.925 AMU. So we have to go through and do this because we cannot count the individual atoms that come through. Okay. What if I gave you, or then if we punch this into the calculator, we should end up with a number that theoretically hits 69.72. Did that math awfully fast. How did I do that math? It's on the periodic table. It's assuming these numbers are actually legit, which is questionable, but okay. So how could I change this around on the exam? I can give you the average. You have the average in front of you. It's on the board or on your periodic tables. So what I could ask is, what is, gallium has two isotopes, 169, 171. If the 71, if I give you these masses, if the 71 happens to be 50%, what is the percentage of the gallium-69? Right? You'd have to go, oh, yeah, way to pick an easy number. 50%. Okay, so you could figure out those percentages relatively quickly. Right? One extra step that we'll mention as you pack up and leave. If you have only two isotopes, what should your percentages total to?
100.
Why 100%? There's only two things. It's got to total to 100%. Okay?